Hello and welcome to this lecture 3 of module on ODE boundary value problems. The type of problems that we have been solving in this particular module are for example we have looked at heat conduction in a rod, and in that particular case the problem that we ended up with was dt by dx equal to some function of t dt by dx, or rather dt by dx square is some function of t dt by dx and x. Okay. And the way we said we can solve this particular problem is by two methods. One which we considered in the previous lecture was the shooting method, and the method that we are going to consider in this particular lecture is through using finite differences. Okay. So in shooting method what we did was converted in shooting method we converted this ODE boundary value problem into ODE initial value problem. Okay. And in that particular case we guessed a value of for the initial value, and based on that guess of the value we tried to see how close we get to the actual boundary value in this particular problem. If we are far away from the boundary value or not close enough from the boundary value, we use either a bisection rule or a Reguli-Falsy method or Newton's method in order to change our initial value such that the boundary values are met. That is the strategy that we followed in shooting method. Now this strategy we saw that worked for the heat conduction problem, where we had the problem of d square t by dx square equal to some linear function. In today's module, first what I am going to do is take up an example where the shooting method is not going to work. The second example that we had spoken about in the first lecture itself was a reactor with axial dispersion, and that was our example 2. And so that was based on a modification to the example that we had done in ODE initial value problems. The PFR, the plug flow reactor example we considered in ODE initial value problem was of the form V dC by dx, where C is concentration, is going to be equal to minus K multiplied by C to the power 1.25. Okay. So this was the example that we had taken in the previous module. Now this we can modify in presence of axial dispersion. We will have another term which corresponds to the axial dispersion term, and that axial dispersion term will be of the form d, which is the dispersion coefficient multiplied by d square c by dx squared. Okay. And now with this, the original initial value problem was what I have written in white, with the initial conditions given as c at 0 is going to be equal to some value c0. Now with this d square c by dx square also included, our boundary condition, we will need a second boundary condition, and typically the second boundary condition is, as we had seen, c dash l equal to 0. Okay. So the first derivative of the concentration C vanishes at the end of the reactor, that becomes our second boundary condition. So the what I have shown in the white color is what we had solved in the previous module. What I am showing in the pink color along with the original equation, that is what the problem is we are going to solve in this particular module. Okay. So I believe the values that we had taken in the previous module was k by v was 1 by 2, and d by v we can take it as 1 by 200. So what I mean by that is substituting the values, we can have this as dc by dx equal to minus c to the power 1.25 by 2 plus 1 by 200 multiplied by c double dash. So that would be the example, and c0 that we had taken in that example was c0 equal to 1. Okay. So what we will do is we will take c to the power 1.25 by 2 on to the left hand side, and we will multiply throughout by 200. So we will get the equation of the form d square c by dx square is going to be equal to 200 times dc by dx plus 100 times c to the power 1.25, okay, and this will be subject to the condition c at 0 equal to 1 and c dash at L equal to 0, okay, and this is the problem that we intend to solve. As we had done before, we will write y equal to c and z equal to dc by dz, which will result in two ODEs. The first ODE, sorry, dc by dx, not dz. This will result in two ODEs. The first ODE is going to be dy by dx is going to be equal to z, and the second ODE is obtained from over here, and that is going to be dz by dx is going to be equal to 200 times dc by dx, which is z, 200 z plus 100 multiplied by y to the power 1.25, okay. So these are going to be our two ODEs, ODE number 1, ODE number 2, which we are going to solve using our initial condition C0 equal to 1 and our C dash 0 equal to a guess value. This is going to be our initial value problem that we are going to solve, such that we finally meet the boundary condition. To arrive at the boundary condition C dash at L equal to 0, okay. So C at 0 equal to 1 I am going to replace as y 0 equal to 1, C dash 0 equal to guess I am going to replace that as y 0, sorry, not y 0 but z 0 equal to guess, and we are going to shoot such that the boundary, we arrive at the boundary condition z at L equal to 0, okay. So this is the problem that we are going to try to solve using Microsoft Excel, and basically what I want to show you is how this particular problem is, this particular way of solving this problem could lead to certain issues that we need to be aware of. So let's create a new problem sheet, a new spreadsheet where we are going to solve this particular problem. Let us go to a new sheet, sorry, and what we are going to do is solve the problem that I just showed on the board. We will increase the size of font size and all those we will increase, okay. So let us try to solve the problem. The problem that we wanted to solve, we would write that as y dash equal to z, and z dash is going to be equal to 200z plus 100y to the power 1.25. Okay, so we will just do format cells and we will just beautify it a little bit. Okay, so this is the problem that we are going to solve with the initial values y0 equal to 0, and let us try certain other initial value, and we will try that for a bunch of initial values and see what happens. Okay, so we will choose our h, let us choose our h as 0.01 as we did previously, or let us choose it as 0.05, let us say, okay, and x we are going to start with 0, and our x I plus 1 is going to be equal to the previous x plus h, and I will do function f2 and put dollar signs over there so that we are fine, okay. Now we require y and we require z. Y is known to us, the initial y is 1, let us say initial z is going to be minus 0.01, that is what z we are going to start off with, okay. And now y dash is equal to z, so we will have k11 is going to be equal to just y dash, sorry, is just going to be equal to z, y dash is equal to z, k1 2 is going to be equal to 200 multiplied by z plus 100 multiplied by y to the power 1.25. Okay, that is going to be our k2, 200 multiplied by z plus 100 multiplied by y to the power 1.25. Okay. Next we want y plus k1 h by 2, so y plus h multiplied by k1 by 2, and we want z plus h k1 by 2. Okay. So this is essentially what we want. So that is going to be equal to y plus, and again this is what we have done in the previous lecture of this module also. So we have y plus h multiplied by k11 divided by 2, and I press F2 over here and edit this by putting dollar signs, so that when I drag and drop our h value does not change. Okay. And this I can just drag it to z plus h k1 by 2, and I will press F2 to figure out that that is indeed, we have z, so that C6 plus h multiplied by k1 2 multiplied by k1 2 divided by 2. Okay. Remember, it is not the whole thing that is divided by 2, but only the h multiplied by k1 guy is actually going to be divided by 2. So this is indeed the correct formula. Okay. Now we want to find k21 and k22, k21 and k22 is to be found, and again this we can get by just copying and pasting it over here. The reason we can get it by copy and pasting is because the relationship of this particular cell with this cell is the same that we need as the relationship between this cell and this cell. So we will just go and do an F2 to see what the value is. So k21 should be equal to z plus hk by 2, and that is exactly what we have our k2 as, and our k22 should be 200 multiplied by this value plus 100 multiplied by this value to the power 1.25. So let us do F2 and see indeed whether that is true. So 200 multiplied by this guy, which is what we ought to replace this with, plus 100 multiplied by this guy to the power 1.25. So y is being replaced by y plus h k1 by 2, and that is indeed what we have over here. Okay. Actually so this F6 is y plus h k1 by 2 and G6 is z plus h k1 by 2. So which is indeed what we need for our problem. Okay. So our y, the new guess, is going to be equal to previous one y plus h multiplied by k21. Okay, and we do F2 and put dollar signs over here, and we should have it correct. Now this z is going to be equal to z plus h multiplied by k22. Okay, and again I will press F2 and put dollar signs. This is what we have been doing all throughout. Okay, so there is nothing odd or nothing new about it. So we will just drag and drop this to the next row, and we need to solve this up to say x equal to 10, let us say. So we will just drag this until we think it should be enough. So that is x equal to 1, let us just go down, and okay, so let us do this up to x equal to 2, let us not even go up to 10, and that is enough for me to show you what the problem is. Okay. So let us say we chose the value of z equal to minus 0.01, and quickly you will see that this particular method is diverging. This, why we get this as an error over here is because the number that we would get over here based on the numerical value should be infinity. Let us try another value z equal to 0 and we will see the same problem. Let us try z equal to 5 and we will see the same problem. So let us say z equal to 0, we will see that after about 1.2 meters of length we get the concentration predicted as infinity. So now if z, let us say we increase it to 5, which is not a correct value because of reaction the concentration should be decreasing, but if you go and check again we have this guy as going to a very large value again. Okay, so what that means is basically if our initial guesses are not in the correct ballpark or not in the correct direction, there is no way for the method that we are going to follow, the shooting method, to really figure out that this is the wrong steps that we are trying to take, and there is no way that one could recover from this type of errors simply because the method has not converged and indeed it has diverged. So what we need is z should be a fairly large negative value. Okay, so let us try to make this value as 10, as minus 10, and if we make this value of as minus 10, our y value becomes negative, and so immediately our k1 becomes square root of, we are trying to take a square root of a negative number, and therefore it does not work. So maybe we have gone too negative, so let us try to go to say minus 5. Okay, minus 5 also does not work because this value immediately has got a negative. Let us say minus 2, how it works. Minus 2, well, this value sounds reasonable, but this value has immediately gone negative. Again minus 2 is not working, so let us try minus 1.5. Again we have the same type of a problem. Let us try minus 1. Again we have a problem after the second iteration. Let us try minus 0.5, and okay, with minus 0.5 it worked for 2 iterations, but it did not work beyond this 2 iterations. So what I am trying to show over here is we take smaller and smaller values, and still, so now with minus 4 we are going to infinity, but with minus 5 if we see minus 0.4 we are going to infinity, but with minus 0.5 we are going to square root of a negative number and the method cannot continue. So this is one of the biggest problems with the shooting method, is that it is a method that is oftentimes it fails to converge. The initial value problem that we can get through a shooting method, the initial value problem itself may not be solvable. The reason that initial value problem may not be solvable is because the eigenvalues of the problem that we will end up with might, either one of the eigenvalues or multiple of those eigenvalues might be positive, which basically means once we start off with a solution, that solution is going to diverge, and at certain point that solution is going to diverge to infinity or minus infinity. So unless we can get a solution or we can guarantee a solution of an initial value problem, we will not be able to proceed with the shooting method. And this is not actually limited to just this particular problem that I showed you. It is not just limited to the axial dispersion problem. This type of problems do happen. For example, in the heat conduction problem, if we add up say a heat generation term, let us say there is some kind of a heat generation because of electrical heating at the center of the rod or something like that, some of those heat generation terms themselves might lead to the same type of instability that we saw with the reactor. Likewise, if there is radiation within this particular system, the radiation problem itself has certain amount of non-linearities associated with t to the power 4 term. That radiation non-linearities are also going to cause some problems with the shooting method. So the overall crux of the matter is that while shooting method is indeed going to work in certain specific examples, shooting method does not work in certain other examples. And the method of analysis that we took up in the ODE initial value problem in the previous module, that is the method of analysis that you need to choose in order to figure out whether the ODE initial value problem is going to converge or not. Typically the problems in shooting method happens because of the ODE initial value problem not converging. Usually if the ODE initial value problems are going to converge to certain solutions, then we can actually get the algebraic equations part to converge. For example, we can use a bisection method which is guaranteed to converge, or even the Newton-Raphson's method or a fixed point iteration type of a method if we are going to use. Those problems tend to be often well behaved that we can indeed go ahead and use the shooting method. Okay. So that is all I have to say about the shooting method.